So I want to start where we left off, which is like, all right, why are we doing all this stuff about Laplace transforms? What does it have to do with differential equations? And the answer is that we can actually use Laplace transforms to solve differential equations. And there's a very, what I would consider a very simple process, which is to say, okay, you start with a differential equation, you take the Laplace transforms of both sides. And we can have tables and various rules for derivatives. So when I talk about rules for derivatives, I mean, in particular, we know how to take the Laplace transform of x prime of t and x double prime of t. And the punchline, which we mentioned last time, is, you know, when we take these derivatives and take Laplace transforms, it turns into introducing these polynomials at the start. S squared. So everything's becoming polynomial problems, which is what algebra is really good at. We say, well, okay, let's flex our strong algebra skills, and we solve for our transform of our answer. So we basically say, okay, we've turned our problem into an algebra problem in step 1. We do the algebra problem in step 2, well, some of it. The algebra problem in step 2 is isolate your x of s. Then, of course, the really fun algebra part is to simplify the expression. And when we say simplify, we say, well, we want to be able to go back. Looking ahead in step 4, it says take the inverse Laplace transform. So we need to make sure that our pieces that we have look like things that are on our table. Because that's the only hope we have of taking the inverse Laplace transform. It has to look like something on our table, which often means we have to pull things apart, which our big tool for pulling things apart, especially when we have lots of things in the denominators, which is what's going to be showing up, is partial fractions. So that's our big topic for today, is partial fractions. But really, we also want to make sure we understand this process. So we'll start with a relatively clean example. Given x double prime minus 6x prime plus 13x equals 0. X of 0 equals 4. X prime of 0 equals 12. So this is an initial value problem. And I want to emphasize, whenever we're using Laplace transforms, it has to be an initial value problem. If you don't have an initial value problem, you can't use Laplace transforms. Okay. So use Laplace transforms to solve for x. Now this is a problem that we could do without Laplace transforms, but we want to, we have our new toy. We want to take it out and play with it and have fun. All right, so what does this entail? Well, we have our process here, so it's like, all right, let's work the process. So we have our differential equation here. What's our step 1? Yeah, it's right there. It says step 1, take the Laplace transform on both sides. Yeah, so we're going to take the Laplace transform of both sides. Now, we actually haven't talked about what the Laplace transform of 0 is, but I think you can probably guess. Yeah, 0. Okay, good. Whew. All right. Now, well, of course, the rest of this, we use linearity. So it's Laplace transform x double prime minus 6 Laplace transform of x prime plus 13 Laplace transform of x equals 0. Okay, and now we start just working our way through this. Now, when I say work our way through it, we come down to our rules for derivatives. They say, okay, so Laplace transform of x double prime. This part would be our s squared capital X. So I'm using the capital here to indicate that's the Laplace transform of it, minus s times x of 0. Well, what is x of 0? It's 4. So minus 4s minus x prime is 0, which is 12. Okay, so that's the Laplace transform of x double prime. Now we go to our next term, which is the Laplace transform of x prime. We don't forget about the 6 in front. Now, here's a time when, of course, it's easy to lose things. So we're going to introduce a really cool idea called a parenthesis. And so the parenthesis is just here to help us remember that the 6 is going to multiply through. I know, it's amazing. It's cool. Okay, so we're going to x prime. So that's s, capital X, minus x0. So minus 4. And then we close parentheses. And now rounding the corner, our last piece. Laplace transform of x, well, that's just capital X. Okay, so we've taken the Laplace transform of both sides. So that's the end of step 1. Now we get to step 2, which is solve for x of s. All right, well, how do we solve for x? What are the steps here?
Isolate.
Yeah, isolation. So one thing we do, say, well, let's find everything with this function x. So we do that, and we say, okay, well, I see an s squared attached there, a minus 6s, and a plus 13. And now you might be thinking, hey, s squared minus 6s plus 13, that looks an awful lot like the polynomial we would encounter if we were doing the characteristic polynomial for that differential equation. Coincidence? I think not. Yeah. Okay. So then everything that doesn't have the x attached to it moves across. Okay, so what doesn't have an x? Well, this minus 4s. When it moves across, it becomes a plus 4s. Then we have this minus 12, and then we have this plus 24, right? Because the minus 6, minus 4 becomes plus 24. So minus 12 plus 24, together they'd make a positive 12 on the left. We move it across, negative 12. All right. Well, to get x by itself, we now just divide by what's in front. So capital X is 4s minus 12 over s squared minus 6s plus 13. Okay, so now we're done with step 2. We're halfway through, which is good because we've used up about half our space here. Now, step 3, simplify, the fun part. Now, okay, looking at this, let's start with our denominator. Does it factor? Doesn't seem to factor. And it doesn't factor in a nice way. So what does that mean? What should we do? Complete the square. I like that answer because it's a good answer. Yes. When you can't factor, complete the square. So what's going on with complete the square? So let's start with our denominator. We say, well, I have s squared minus 6s, and then what would I need to add? So remember, you take the middle term, divide by 2, and you square that, plus 9. You might say, well, wait, it's supposed to be plus 13. Okay, plus 4 more. It turns out 13 does in fact equal 9 plus 4. True story, true story. Okay, so a 4s minus 12. Now, downstairs, this becomes s minus 3 squared plus a2 squared. How about the upstairs? Should we do anything there? Yeah, factor out the 4. 4 times s minus 3. And remember, when we're simplifying, we ask ourselves, have we gone to things that look like what's on our table? So we pull out our table. See, here's our table. It's all sorts of good stuff. And my eye is drawn to this left-hand side. So, let's see. Does 4 times s minus 3 over s minus 3 squared plus 2 squared look like anything on our table? Yeah, what does it look like? E to the ct cosine bt. So we say, okay, in fact, we can really write this as 4 times. We'll pull that out as a constant. So we have an s minus 3 squared plus 2 squared. And now we say, okay, so we've successfully simplified to match something that's on our table. So the last step is to say, all right, our answer, little x, the solution to the differential equation, is the inverse Laplace transform of big X. Well, the 4 comes out, and we just make sure we copy from our table correctly. So as a reminder, we said it was e to the 3t, because c equals 3, cosine 2t. So 4 e to the 3t cosine 2t. All right, are we done? Yeah, we've run out of steps, right? So that's a good sign that we're done. What about the initial conditions? They're already in there. See, the initial conditions are taken care of at the beginning of the process, not at the end of the process. You know, if this was a horror movie, we would be saying the initial conditions are coming from inside the house. You know, they're already there. So, all right, so there we go. That's the process. So good. We know how it works. So, what do we need to talk about? Well, our goal is we're going to delve into partial fractions. Now, this will be a little bit of a deja vu. And the reason I'm going to say it's a little bit of a deja vu is I copied this slide from Calc 2. Now, you might say, oh, partial fractions is a Calc 2 thing. No, it's an algebra thing. Hopefully you saw way back when you took algebra many, many months ago. For me, it's decades now, but it's nice to be young. So what's the idea? Well, the idea is you have a challenge in that you want to pull things apart because naturally that's what you'd like to do. So as a simple example of what I mean by pulling things apart, maybe you have something like 1 over x squared plus x. You say, you know, I would like to somehow simplify this expression. Now, of course, the dangerous thing to do is what? 1 over x squared plus 1 over x. Now people are like, that doesn't seem very dangerous. That's what I think you should do. Except it's not true. See, not equal. All right. You have to be really careful because fractions are weird. They don't work like you think they should do, right? So say, for example, like 64 divided by 16. What do? You cancel the 6's, right? And you're left with 4, which of course doesn't work. Doesn't work that way. That's not how fractions work. Okay, that's not a good example, but the point is, you know, fractions don't work the way that you think they should. So, okay, all right. So you might say, well, okay, if you can't do this, what can you do? I mean, how do you simplify this? Well, the right way to go is to say, well, this is really 1 over x times x plus 1, because x squared plus x you can factor fairly nicely. And it is the case that this can be written as a combination, as something over x and something over x plus 1. And then, of course, the hard part is to figure out what goes where. Well, in this case, it turns out it's equal to that. So this is what we mean when we talk about partial fractions. It's that ability to somehow pull it apart. We're pulling the denominator apart. That's the goal. And so that what's left is easier to work with. Okay, so how does it work? Well, the idea is you say, all right, you have your denominator and you factor it. And you have pieces that look like s minus something to a power, or maybe you have things that are not factorable, but you can do completing the square. So you have things that look like what we would call irreducible quadratics. Whenever you have s minus something to a power, you get pieces that look like a constant over s minus c, constant over s minus c squared all the way up to some constant over s minus c to the k. When it's irreducible quadratic, it's a little bit more exciting. Upstairs, it's not just a constant, but a constant times s plus a constant. And again, you work your way all the way up. Now, these constants have to be determined. They're not known before you start. And so you have to figure out, well, what are they? Well, how do you figure it out? There's a lot of ways to do it. And so to determine the constants, what I like to do is I say, okay, I have my expression. We're going to do some practice in just a moment here. We have our expression. Clear your denominator, which means multiply both sides so that there's nothing downstairs. So that says you have polynomial versus polynomial. And once you have polynomial versus polynomial, you start saying, okay, what are things that have to be true about polynomial versus polynomial if they're equal? Well, one thing is they have to have the same coefficients. So you say, all right, set your coefficients equal to each other and solve. That leads to a system of equations. Maybe 2 equations, 2 unknowns, maybe 8 equations, 8 unknowns. Just depends on how many unknowns you have to solve for. I like it, and personally, this is my preferred method. So I would strongly encourage you to do number 2, which is just to say 2 polynomials are the same if they're the same at every point. So choose wisely. Whereas a good choice will make many things vanish. A bad choice keeps all the terms there. So choose things that help knock terms out. So this is great for quickly determining a few values, and oftentimes you can reduce down to just 2 or 3 left that you have to figure out. The last thing says, all right, 2 polynomials agree if and only if their derivatives agree at all points. And so you just start taking derivatives and plugging in, again, choosing wisely. This is somewhat more specialized, but it's a really cool way if you ever have something where your partial fractions is something upstairs and downstairs, it's s minus something to a power. And depending upon how much time we have, we'll see all of these. All right, so I'm not going to spend too much time on partial fractions. The theory, I want to spend it on partial fractions, the practice. Are there any questions before we jump into the practice? Hopefully you've seen this before, so it'll come back to you. It's like riding a bicycle. It comes back. All right. Example. Find the partial fractions decomposition of the expression 10s cubed minus s squared plus 10s plus 9 all over s squared plus 1 times s minus 2 times s plus 1. On a side note, if you remember back to Calc 2, those good old days, you might say, hey, when we did partial fractions back then, we always had to be like, do I need to divide? I can tell you now, you don't have to worry about that. You'll never have to divide. So that's good news for us. All right, so what's the process? Well, the first step is to say, look at the downstairs and factor it. Well, okay, that was pretty quick. It's already factored for us. Thank you. And now we say, okay, for each piece, we have to say what's the right term. So s squared plus 1. So that says my decomposition. There's going to be an s squared plus 1 downstairs. What will the upstairs look like? An as plus b. Because this is irreducible quadratic, I can't factor it. I have to have 2 terms upstairs. And now I keep moving my way across. Say, okay, there's an s minus 2 here. So I'm going to have an s minus 2. And what will be upstairs? Indeed, some constant c. And I keep going, and I say, okay, there's an s plus 1. So I'm going to have something over s plus 1. What goes up above it? D. And there we go. So there is some choice of A, B, C, D where this is true. And now our goal is to figure out what is the right choice for A, B, C, and D. All right, so that is actually one of the hardest things we just did, which is get the right form. So usually after that, it's a lot of just patience and working it through. Do you remember what the next thing is after you have the right form? Yeah, we got to multiply the bottom through because we want to clear our denominators. Now you might say, well, what do we multiply by? And the answer is whatever the denominator is that you started with. So everything's going to get multiplied by s squared plus 1 times s minus 2 times s plus 1. Everything. Now on the left-hand side, what's left? The numerator. So we have 10s cubed minus s squared plus 10s plus 9. Okay, equals, on the first term, well, I'm multiplying by these three pieces. I have an s squared plus 1. Downstairs, what's going to be left? Well, the s squared plus 1s cancel. So we're left with the as plus b. And then we have to multiply by the parts that didn't cancel. S minus 2, s plus 1. Yes? Yes, it is true. Okay. Plus c. Now, here, the s minus 2's cancel. So we're left with the s squared plus 1 and the s plus 1. And finally, on the end, the s plus 1's cancel. So we're left with the s squared plus 1, s minus 2. Okay, so there we have our wonderful expression. Polynomial on the left, polynomial on the right. Now we start chipping away. We've got to figure out four things. What are A, B, C, and D? So, how would you like to proceed? Plug in values of S. Okay. I do like to start with the choose wisely approach because I like it. So is there a good choice for S? 2. Okay, someone has suggested that 2 is a good choice. Now, why is 2 a great choice? Well, what happens to the first term? 0. What happens to this last term? 0. So when we plug in 2, there's the term here and the term there, which makes things a lot easier. Other than we have big numbers here, but that's okay. We're not intimidated by big numbers. 10 times 8 is 80, minus 2 squared is 4, plus 20, plus 9 equals C times 5 times 3. Okay, so 80 plus 20 plus 9 minus 4, also known as 105, equals 15 times C. So C is 7. That wasn't so bad. Is there another choice? -1. Okay. So we now will choose S equals -1. Now, -1 knocks out the first and the second blocks. Okay, so -1 cubed makes it negative, so that's -10. -1 squared is -1. And then a -10 and a plus 9 equals, okay, let's see, gone. The last part we have is D times 2 times -3. Okay, -10 minus 1 minus 10 plus 9. If we put that all together, we get -12 equals -6D. So D is 2. Progress. Is there any other nice number? Well, pi is a nice number in its own way, but probably not for this. 0 is actually a nice number. Now, I know you're thinking like, 0, that doesn't cancel anything, except it does. See how they have an a times an s? Like, okay, I'm willing to go along with this 0 thing. So s equals 0. Okay, 0 minus 0 plus 0 plus 9. Oh, okay, 9. Equals 0 plus b, which is b, times minus 2 times 1, plus c times 1 times 1, plus d times 1 times negative 2. And you're like, aha, Steve, see? You don't know c and d, do you? Like, oh, wait, yeah, we do. So we have, this is negative 2b. C is 7. Then D is D is plus 2 times minus 2 makes minus 4. All right. Well, that can be rewritten as 9 minus 2b plus 3. Okay, 6 equals minus 2b. So what is b? B is negative 3. All right. Well, that's progress. It really is good progress. All right. Well, anything else that we can do? We could do I, but that sounds complex. So, but actually the thing is, at this point we have 3 out of 4. Any number can help us get our last one. Is there a nice number we haven't picked yet? Yes. 1. You guys are budding mathematicians. You know, like, given a choice of number, 0 or 1. Okay, so 1. Let's do it. Let's finish this problem. Okay, so we have 10 minus 1 plus 10 plus 9 equals a plus b minus 1, 2, plus c, 2, 2, plus d, 2, minus 1. So I'm just plugging in 1 really quickly. But of course, we'll update this because we know things. 10 minus 1 plus 10 plus 9 gives us 28. Then we have a minus 3 times negative 2. C is 7, so we have 7 times 2 times 2, which is 28. And then D is 2, so we have minus 4. Well, this is kind of convenient. The 28s cancel. So let's see, that says 0 equals minus 2a plus 6 minus 4. So I'm just distributing the minus 2 through. Or 2a equals 2. So a equals 1. All right, so our question was find the partial fractions decomposition. We found a, b, c, d. So our final answer is just to put it all together and we'll be done. So we have s, because a is 1, minus 3, since b is minus 3, over s squared plus 1. Then plus c, which is 7, over s minus 2, plus d, which is 2, over s plus 1. Okay, so there's our partial fractions decomposition. Oh, good, good. All right, any questions about that? Well, great. In that case, let's combine these two ideas and find the inverse Laplace transform, 3s plus 1 over s squared minus 4s plus 3. So the combined ideas means like the process of like solving a differential equation. We might encounter this. So what's the process? Well, the first thing that we should do when we see a problem like this is start where? Start in the denominator. Does it factor? As how? Yeah, -3 and -1. Okay. So you factor s minus 1, s minus 3. The next step, break it up. Partial fractions decomposition. So it's something over s minus 1 and something over s minus 3. Clear your denominators. So when we talk about clear your denominators, what we really mean by that is we're multiplying everything by s minus 1, s minus 3. So you get the numerator that you started with, a times s minus 3, b times s minus 1. And I'm assuming people were like, I'm going to choose wisely because I like myself, and it's the easier way to solve this, which is great. And choosing 1 and 3 gives you the answers for a and b, which really lets you say, we haven't done anything with the Laplace transform, but what we've done is we've rewritten it in pieces which are nice. And 1 over s minus a number is on our table. In particular, 1 over s minus a number is e to that number t. So that allows us to get our answer minus 2e to the t plus 5e to the 3t. By the way, we probably should mention in passing, what if you didn't like to do this I'm going to plug in numbers thing? What if you want to do the coefficients matching thing? Because I do want you to see that, that technique does show up. The way it works is you group coefficients together. So you have 3s plus 1 equals as minus 3a plus bs minus b. Well, that's a plus b times s plus minus 3a minus b. And now the idea is you compare coefficients. So for example, the 3, that's the coefficient for s. That should also match the coefficient for s on the other side. So you get a plus b equals 3. At the same time, the 1, which is your constant, will match your constant term there. So you end up with minus 3a minus b equals 1. And then you get a system of 2 equations and 2 unknowns. And you can solve for a and b. So this is the other way to solve for a and b. So just so we all agree. All right, good. So you're ready for these types of problems, yes? All right, let's kick it up a notch. Not partial fractions, right? We'll go back. We talked about this process. So solve x double prime minus x prime minus 2x equals 10 sine of t, x of 0 equals 10, x prime of 0 equals 9, and for an added challenge, do it before time runs out. All right, I like the added challenge. Okay, so where do we start? What's our first step? Yeah, take the Laplace transform of both sides. We know that because it says it right here. All right. Now, on the test, it won't give you this. So hopefully you learn the process between now and when the test happens. All right, so we're taking the Laplace transform of x double prime minus the Laplace transform of x prime minus 2 Laplace transform of x is going to be equal to 10 Laplace transform of sine t. So this is taking Laplace transform and using the fact that things are linear. And now we say, okay, we look at our table. So for example, if I want the Laplace transform of x double prime, that's s squared x minus s. I should have updated this. These should be x's here. I'm sorry, I forgot to update this chart. Yeah, s squared x minus s x0 minus x prime 0. Okay, so that says our first piece looks like s squared x minus s times 10 minus 9. So that's our first piece. Okay, now our second piece. And again, we're going to use our point-saving technology called the parenthesis, because there's a minus here. It could be easy for us to forget that minus. Same formula sheet, we look it up, and we see that, okay, x prime becomes sx minus x0, 10. And then we go to our last piece. So we have minus 2x. Okay, now all of that is going to be equal to, lo and behold, 10 times the Laplace transform of sine t. Well, okay, no worries. Sine t made our list. So sine t is going to be 1 over s squared plus 1. Okay. And there we go. There she is. In all its splendiferous glory. Okay, where do we go next? Solve for x. Yeah, see, it's nice. It's telling us what to do. All right, so we get s squared minus s minus 2 times x. Okay, so that's those terms. And then let's move everything else across. So we already have a 10 over s squared plus 1. Here, there's a minus 10s. When we bring it across, it'll become a plus 10s. And here I have a minus 9 and a plus 10, because the minus distributes. So on this left-hand side, it would be a plus 1, comes across, minus 1. So far, so good? Let's combine these terms. So right now it's 10 over s squared plus 1 and 10s minus 1 over 1. So if I wanted to combine, what should I do? Common denominator. So s squared plus 1, s squared plus 1. Okay, so this would be 10. And we get to do multiplication. Lucky us. We have 10s cubed plus 10s minus s squared minus 1 all over s squared plus 1. Okay, so we almost have x by itself. Oh, on a side note, s squared minus s minus 2. Does that factor nicely? S minus 2, s plus 1. Yeah. So we get that x is equal to, now upstairs, this would be 10s cubed, then a minus s squared, because there's a minus s squared, and then a 10s, and then 10 minus 1 would become a plus 9. And downstairs we'd have our s squared plus 1, our s minus 2, and our s plus 1. Okay, so there's x. So, what do we do? What's the next thing for us to do? We do partial fractions of 10s cubed minus s squared plus 10s plus 9 over s squared plus 1, s minus 2, s plus 1. It's almost like we anticipated the problem that would come up. Okay, so by partial fractions, also known as copying the previous work, s minus 3 over s squared plus 1 plus 7 over s minus 2 plus 2 over s plus 1. So, let's see. Should we do anything to rewrite this even more than it already is? In other words, are all these things on our table? Well, I would do just a little bit more. This first term I write as s over s squared plus 1 minus 3 times 1 over s squared plus 1 plus 7, 1 over s minus 2 plus 2, 1 over s plus 1. The big thing here is breaking up the first part. Because when we look at our table, s over s squared plus 1 is good, and 1 over s squared plus 1 is good, but not like s plus something over s squared plus 1. So we want to separate. All right, so let's go through. S over s squared plus 1. Is that on our table? Well, it is. What is the inverse Laplace of s over s squared plus 1? Cosine. So we have cosine t minus 3. The inverse Laplace of 1 over s squared plus 1, sine t. So minus 3 sine t. Plus 7, inverse Laplace of 1 over s minus 2. E to the 2t. Plus 2, inverse Laplace of 1 over s plus 1. Well, yeah, this is s minus minus 1. So it's 2 e to negative t. And we're done. Now you might say, wow, that was cool. Or you might say, I could have done this another way. But I don't know. I think it's interesting. I really like the process. So we have a few minutes left. So the question is, which one should we talk about? I just want to talk about, we won't have time to finish it, but I do want to talk about one problem for just a second. What if you have systems? Can you use Laplace transforms to work with systems? Well, yeah, you can, because it says use the Laplace transform to help solve this system. So how does it work? What's the idea? Well, what you do is you're going to have a capital X, which is the Laplace transform of little x, and a capital Y, which is the Laplace transform of little y. And now you go and you run it through. So for instance here, this would become s squared capital X minus, okay, x of 0 is 0, so minus s times 0 and minus minus 1. So that's your x double prime plus 2 capital X plus 4 capital Y equals 0. Here, I'll start with the x first, so I get capital X. Then y double prime would be s squared capital Y minus s times 0 minus minus 1. There's that y double prime plus 2 capital Y equals 0. Now, you might be saying, oh, this looks terrible. But wait a second. Check this out. Check this out. Okay. This is s squared plus 2 capital X plus 4 capital Y equals minus 1. And capital X plus s squared plus 2 capital Y equals, and again, minus 1. What can you use here? Kramer's rule. Kramer's rule now. So you can use Kramer's rule, and that can help you solve for capital X and for capital Y, and then you take the inverse Laplace. And, well, actually, that's it. Our time is up.